Okay.
Okay, thank you. So it's a great pleasure today to have Lea Bossmann from IST Austria, and she's going to tell us about asymptotic expansion of low energy excitations for weakly interacting bosons. Lea?
Yeah, thanks to you very much for the introduction, and most of all, of course, for the invitation. It's really a pleasure, and I would like to use this opportunity to talk about the result concerning the mean field Bose gas. So in a nutshell, the content of my talk is the following. So I would like to consider a system which consists of n bosons, and the bosons are confined in an external trapping potential. And the bosons interact with each other via interactions in the mean field regime. So this means that we have many weak and long-range interactions between the particles. And I always want to study the case where n, so the number of particles, is really large. And in this situation, where we have many interacting particles, we would like to characterize the ground state of the system and also the low energy eigenstates as precisely as we can. So in our main result, we compute the ground state and also its energy to any order in 1 over n. And we can also extend this result to the low energy excitation spectrum. And of course, also to the corresponding eigenstates. So essentially, what we prove is that we prove rigorously that you can apply perturbation theory in this interacting many-body setting. Okay, and then the next question is the question concerning the dynamics. So we would like to switch off the trap, and then we would like to monitor the time evolution of the gas. And what we see is that the structure of the ground state and also of the low energy eigenstates is preserved by the dynamics. So the first part here, concerning the spectrum, that's joint work with Sören Petrat and Robert Seiringer. And the second part, concerning the dynamics, that's joint work with Sören Petrat, Peter Pickl, and Avy Soffer. Okay, so now here's the model in some more detail. Okay, I've written here the n-body Hamiltonian. So we want like to consider particles in d-dimensional space. And therefore, they are non-relativistic particles, so the kinetic part is simply the Laplace operator acting on the jth component. Okay, now the particles are confined in a confining trap, which is Vx, and we essentially only assume that it should be confining, so this means that it has to diverge as x goes to infinity. So for the sake of this talk, simply think of a harmonic oscillator potential. Okay, now we have the particles in the trap. Now the particles should also interact with each other, and they do this via pair interactions V. And I would like to assume V to be even, bounded, and of positive type. Actually, we will see later that we do not really necessarily need the boundedness assumption, but for the moment, I would like to start in the simplest setting, and I will comment about unbounded interactions later. Okay, now these bounded pair interactions, they are now rescaled by a scaling parameter lambda, or lambda n. And lambda n is a shortcut for 1 over n minus 1. And this rescaling makes everything a mean field regime, because this means we have very weak interactions, because we essentially divide by n, and n is supposed to be large. And the interactions are also long range, because they live on the length scale of the trap. Again, this is actually known as the Hartree scaling. Okay, now we would like to consider the ground state of the system, and the ground state is called psi n. And since we have bosons, this will be a symmetric n-body wave function. And we choose it normalized, so the norm of psi n equals 1. So later on, I will also be considering lower energy excited states, but at the moment I would like to start in the simplest setting, which means that we would have only bounded interactions and we consider only the ground state. Okay, so and we denote by the ground state, it's unique, and we denote by Pn the spectral projector onto the ground state. Okay, now this Hamiltonian here, this has been really studied quite a lot, and a lot of things are known about it. For example, it's known that there's Bose-Einstein condensation in the ground state. And heuristically speaking, Bose-Einstein condensation means that essentially every particle is in the same state, in the same one-body state, phi. It's also called the condensate wave function. And in our case, phi is the minimizer of the Hartree energy function. Mathematically speaking, Bose-Einstein condensation means that Pn, so the projector onto the n-body ground state, this is close in a certain sense to the projection into a state where each particle is in the state phi. Okay, and close is here meant in the sense of reduced densities. Now, so this means basically that the great majority of all particles is in the state phi, and this means that we can compute the leading order contribution to the ground state energy. So I've written here the ground state energy, that's the trace of Pn Hn. And so because of this approximate sign here, we know that the leading order of this is given by the expectation value of the Hamiltonian Hn with respect to the state where each particle is in the state phi, so the factorized state. Okay, and if we compute this, then we get n times a constant. The constant is called EH. Okay, but this only holds approximately in the sense of reduced densities. And this means that we will have an error term here, and the error term is of order 1. And the reason for this error term, the physical reason, is the fact that we have interacting particles. And because we have interacting particles, the ground state is not exactly the factorized state, which means that every particle is in the condensate state. But because of the interactions, not every particle is in the condensate state, but there will be excitations from the condensate. And these excitations are exactly the reason why we get an error term here. So now the goal in this talk is now to compute this quantity here, the ground state energy, as precisely as we can. So in other words, we would like to resolve this order 1 error term here. And since this is the energy which is contributed by the excitations, we need to have a look at the excitations. So I've written here, we use now a technique proposed by Levine, Nam, Sefati, and Solovay in 2015. Namely, we split the n-body wave function into a condensate part and excitations from the condensate. So here we have a state where n minus k particles are in the condensate. So this phi is the condensate wave function, and k particles are orthogonal to the condensate. So chi k is a k-body wave function, which is orthogonal to phi in each coordinate. Now we take the symmetric tensor product between the two, and we sum from k equals 0. So this would mean that each particle is in the state phi and no particle is orthogonal, up to k equal n, which means that no particle is in the condensate and each particle is orthogonal to it. And now we can write all these excitations a bit more compactly in form of a Fock vector. So we can write this Fock vector, so we construct this Fock vector by filling the first slots by chi0 up to chi n, and then we fill all other slots up by 0. And in this way, we have constructed an element of a Fock space F perp, so that's the Fock space over the orthogonal complement of phi. Okay, and last but not least, we denote by P the projector onto chi. So now maybe I summarize the notation first. So psi n is the n-body ground state, chi is the excitation part of the n-body ground state, and P is the projector onto chi. Okay, now our goal is now to compute this excitation part of the ground state energy. So in other words, we would like to have the next orders after the condensate part of the energy. In other words, we have to extract now the energy which is contributed only by the excitations. And we do this using the excitation map. So that's also a tool from this paper by Levine, Nam, Sefati, and Solovay, namely which maps the n-body state onto its excitation part. We make use of this in the following way. So we have the trace of Pn Hn, that's the ground state energy. But now instead of writing Pn, which is the projector onto the n-body ground state, we can also write P, which is the projector onto the excitation part of the n-body ground state, conjugated with the excitation map. So actually this would be a unitary map if we would map from the n particle space into the truncated Fock space, where we truncate after n sectors. But since the chi are constructed in such a way that we simply fill up all the other slots by 0, we can simply extend un by 0 outside the truncated Fock space, un star, and then makes sense. Okay, so now we write, instead of Pn, we write u star Pu. Then we make use of the cyclicity of the trace to bring u star on the other side. We also add and subtract the condensate part of the energy. And if we do this, then we end up with a formula which looks exactly like this formula. So we've extracted the condensate part of the energy, and this is now really a formula giving the order 1 contribution, which comes from the excitations. So now I denote by H the excitation Hamiltonian. So you get the excitation Hamiltonian by taking the n-body Hamiltonian, subtracting the condensate part of the energy, then conjugating with the excitation map. Okay, and using this notation, we can now write the ground state energy as the condensate part of the energy plus the trace over pH. So this is now really the energy contributed by the excitations from the condensate. Okay, now this is what we want to compute. The first step is now to compute the excitation Hamiltonian. And we can do this explicitly because we know how this map U acts on creation and annihilation operators. Okay, and if we compute this, then we get, after some calculations, a formula like this. So I do not want to comment on all the details, just yeah, point out the important facts about this formula. So we have 5 terms here, and each term has an operator k and a prefactor. So the operators k, they're written down here. So I don't care about the details at the moment. Only like to point out 2 facts. Namely, first of all, these operators k, they are all explicitly known. They are all given in terms of the interaction and the condensate wave function. And they are completely independent of n, the number of particles. But each operator k has a prefactor, and this prefactor is now depending on n and also an n perp here. So that's the, that's the number operator counting the excitations. Okay, now what we would like to do now is we would like to compute the ground state energy of this Hamiltonian. So the easiest idea is to do a Taylor expansion of all these n-dependent prefactors. And if we do this, then we get formally an expansion of this Hamiltonian in powers of lambda to the 1/2. So recall that lambda was this prefactor in the Hamiltonian 1 over n minus 1. And so if we get an expansion in powers of lambda to the 1/2, but that's only formal because we don't know whether the series will converge if j goes to infinity. But actually we won't care about this because we will always expand up to some order, and then we truncate the Taylor expansion and we estimate the Taylor remainder. Okay, so formally we have now this expansion of the Hamiltonian. And so now I would like to comment on the leading order term, the H0. So if I go back here to the formula for H, then we see that each term here in the first line has an order 1 contribution. So we have a K0, K1, K2, and K2 star. And in the second line, everything is subleading. So if I now collect all the order 1 terms here, then we get exactly the leading order H0, and that's what's known as the Bogoliubov Hamiltonian. So that's a very well-known Hamiltonian, which has been first proposed by Bogoliubov in 1947, and since then it has really been used a lot to analyze the Bose gas. And what's very convenient about this Hamiltonian is that it's a quadratic Hamiltonian, which means that it can be diagonalized by Bogoliubov transformations. And what's also very convenient for us is that it's ground state. So I denote the ground state by K0, and it's unique, but most important, it's a quasi-free state. Okay, and then I'll also denote by E0 the ground state energy of H0. Okay, so now if we look again at this formal expansion of the Hamiltonian, we're interested in the ground state energy of this Hamiltonian. And if you look at this formal expansion, then you would of course guess that to leading order, this ground state energy is given by the ground state energy of the Bogoliubov Hamiltonian, E0. And that's actually true and has been proven, but it's not at all easy to prove such a statement because all of these operators are unbounded operators. So it was first managed roughly 10 years ago to show that the ground state energy is given by the Bogoliubov ground state energy up to an error which is of the order n to the minus 1/2. This was first shown in 2011 by Seiringer for the Bose gas on a torus, later by Grech and Seiringer for the Bose gas in a trap. And then there's also a paper which I've already mentioned by Levine, Namsefati, and Soloway, where they also proved the statement, but in a very generic setting, also including unbounded interactions. And actually, I should say that all of these results, they're not only restricted to this statement here, but they also prove really convergence of the states, and they also extend to the low energy excitation spectrum. Okay, so this is essentially what has been known so far, and now I'm going to present the new result. So in our new result, we show that P, so that's the projector onto the excitation part of the n-body ground state, has an asymptotic expansion. So this means that we can expand it in a power series in powers of lambda to the 1/2. If we truncate the series at order A, then we get an error which is of the order lambda to the A plus 1/2. And the coefficients here in this expansion, the PL, they're written down here. So the leading order is of course the Bogoliubov ground state projector, and the higher orders are written here. So they're all of the same form. We get a lot of sums, and then we have alternatingly operators OK and HJ. So HJ, these are the terms here from the expansion of the Hamiltonian. And OK is a shortcut. So for k equals 0, you get minus the Bogoliubov ground state projector. And for k larger than 0, we get the resolvent of the Bogoliubov Hamiltonian at its ground state energy to the power of k, evaluated on the range of Q0, and Q0 is the orthogonal projector to P0. Okay, so for example, the next to leading order, so the first order correction after the Bogoliubov ground state projector is P1, and that's given by the Bogoliubov resolvent H1 P0 plus the Hermitian conjugate. So actually this formula is not at all surprising, because that's really what you get from standard first order perturbation theory. Actually, formally, you could really derive the whole result using standard perturbation theory. Just what makes it long and complicated is that in each step of the perturbation theory, you also have to expand the Hamiltonian one step further. This is why you get all these combinatorics here. But of course, where the mathematical work goes in is in proving an error estimate like this. Okay, so now what we have for here is now an expansion of P, and P is the excitation part of the n-body ground state. But what we're really looking for is an expansion of the n-body ground state itself, and that's how we formulated our main result.
Oh, sorry, just a question. Are you going to comment on the constancy of A? Do you know how it grows with A?
Yeah, I wanted to comment later, but I can already say now it's horrible. So it grows very fast in A. It's like e to the A factorial, so really terrible. So you obviously have to read the statement like fix A and then let n be large enough. Yeah. Thanks.
And do you have a guess on what could be the optimal constant?
I just think that with our methods we will not get the optimal constant. But maybe I comment on this a bit later when I state the main result. But thanks for the question. Yeah. Okay, so maybe now it's a good time to get to the main result, which is essentially the same, but for the n-body projector. So I will denote by AM a symmetrized n-body operator, and then the main result is the following. So we let AM be any self-adjoint symmetrized n-body operator, which is relatively bounded by the Laplace operator plus the external potential. And then we get the following statement. So we'll fix any A, and then we get that the ground state energy of this, the ground state expectation value of this operator AM, it has an asymptotic expansion. Namely, we get a power series expansion in powers of lambda to the 1/2. We truncate the series at order A, and then we get an error estimate, which is of the order lambda to the A plus 2/2. So recall that this is 1/2 better than we had on the last slide, and I will comment on this later. Okay, now the coefficients here in this expansion, there you get them by taking the operator AM, conjugating with the map U, and then taking the trace against the PL. So these were the operators here from this last slide. Okay, now maybe before I comment on this result, I would like to mention related results in literature. So there's a series of 3 papers by Alessandro Pizzo, where he also constructs an expansion of the ground state for a Bose gas, but in a very different setting and also using very different methods. And then there's a statement by Namen Napiorkovsky, where they prove that for the ground state of the Bose gas in the torus, they prove the first order correction to the reduced one particle density matrix. Actually, we could also reformulate our result in terms of reduced densities, and then we would exactly get their result back if we go to the torus. Okay, now I wanted anyway to comment on the dependence on the constancy of A. So this really grows very rapidly in A. It's definitely not optimal because there are related results for the dynamics, which show that you can get Borel summerability. We can definitely not get this with our method. So therefore, I think it cannot be optimal at all. Yeah. Okay. And anywhere, what else did I want to say? Ah, yeah, right, about the n dependence. So in this result here, like so we have an n dependence here in the prefactor, but we have also an n dependence here because we have an operator on n-body Hilbert space, and we conjugate this with a map, which is also depending on n. If we now would like to get a series expansion where the full n dependence is only in the prefactor, then we would have to expand this again in n. So the simplest example is maybe if you take the n-body Hamiltonian, because that's a symmetrized 2-body operator. And if we conjugate the Hamiltonian with this map U, then we get essentially the excitation Hamiltonian, which had these explicitly n-dependent prefactors. So in order to get something which is really where only this prefactor depends on n, we would then have to expand this again in n and then sort the terms accordingly. And this is exactly what we did in our second main result concerning the ground state energy. So in our second main result, we prove now that the ground state energy of this n-body Hamiltonian Hn, okay, we know to leading order, it's given by the condensate part of the energy. The next order correction is the Bogoliubov ground state energy. And then we get higher order corrections to this. Namely, we get a power series in powers of lambda. We truncate at a, and then we get an error, which is of the order lambda to the a plus 1. So now this is a power series now in powers of lambda, not in powers of lambda to the 1/2. In other words, all the terms with the prefactor lambda to all the half integer powers of lambda vanish. And in order to see this, you should look at these coefficients EL here. So they're all of the same form, that we get a lot of sums, and then we have the trace of P0 against Hj, Om, and so on. So Hj were the terms from the expansion of the Hamiltonian, and Om is either a Bogoliubov ground state projector or it's a Bogoliubov resolvent. And now there's one fact about the operators Hj, which I did not mention before, namely if J is odd, then Hj contains an odd number of creation and annihilation operators. And if Hj is even, then it contains an even number of creation and annihilation operators. And now this explains why the half integer powers of lambda vanish, because if you have a half integer power of lambda here, then all the j add up to something odd. So this means that in total we get an odd number of creation and annihilation operators in the trace, but we take the trace against P0, and that's the projector onto the Bogoliubov ground state, which is quasi-free. This means that the expression vanishes by Wick's rule. So in summary, we get only all the integer powers of lambda here. So for example, the first order correction to the Bogoliubov energy, the E1, that's given by the expectation value of H2 plus the expectation value of H1, Bogoliubov resolvent H1, with respect to the quasi-free state Chi0. And again, this is not surprising because this is what you get from perturbation theory. And maybe as a nice side result, we have now also shown that the Bogoliubov ground state energy, this approximation is not only good up to an error of the order n to the minus 1/2, which has been known before, but really up to an error which is of the order n to the minus 1. Okay, so this is essentially the main result. Now I would like to say some words about the strategy of proof. Okay, so the main idea is, we start with writing the projector P, so the projector onto the excitation part of the n-body ground state, as the resolvent, an integral over the resolvent of the excitation Hamiltonian along a contour which only contains the eigenvalue E. So E is now a shortcut for the ground state energy, and it does not contain any other eigenvalue of H. And analogously, we also write P0 as the integral over the resolvent of H0 along a contour which only contains E0, so the Bogoliubov ground state energy, and no other point in the spectrum of the Bogoliubov Hamiltonian. Okay, but now we know, for example, by this result by Grech and Seiringer, that E converges to E0 as n goes to infinity. And this means that essentially each finite contour around E0 will eventually also enclose E. This means that here we could replace a gamma E by a gamma E0. And then we can also make use of our expansion of the Hamiltonian H to expand the resolvent around the resolvent of the Bogoliubov Hamiltonian. So if we do this, then we get, as leading order, we get the Bogoliubov resolvent, and then we get higher order terms, which are all of the form that we have alternatingly Bogoliubov resolvents and terms from the expansion of the Hamiltonian. And then we truncate this expansion at some point, and in the very last term, we have a full resolvent again, but this will go into the remainder, and I will talk about estimating the remainder later. So for example, let's look at the lambda to the 1/2 contribution here. So if we plug this back into the integral, then we get P1, so the next order correction after the Bogoliubov ground state projector. So here's the formula for P1. Now we can simplify this a bit. The first step is to decompose the identities here as P0 plus Q0. So P0 is the Bogoliubov ground state projector, Q0 is the orthogonal complement. And now if we multiply this out, then we get 4 terms. So let's first look at the P0 contribution. Okay, so in the range of P0, H0 acts as an E0. So therefore, we can pull the operator H1 out of the integral. In other words, everything depending on Z is only a number. So this means we have to integrate over 1 over z minus E0 squared, and this vanishes. Okay, next look at the Q0 contribution. So this will also vanish. And the reason is that Q0 is the orthogonal projected to P0, but E0, so the eigenvalue corresponding to P0, that's the only eigenvalue contained in this contour. So therefore, with the 2Q0, the integrand is holomorphic and the integral vanishes as well. So the only two summands left are the mixed terms, so P0, Q0, and here I already replaced an H0 by an E0 because we are on the range of P0. Okay, now this is an expression which we can now compute using the residue theorem, and we get the result which we already knew. So this formula for P1. And to compute the higher order terms, the PL for L larger than 1, we essentially do the same, just the computations get more complicated because we have lot of terms here, but essentially the ideas are the same. Okay, now what's now left to do and what's the actual mathematical work is to estimate the remainder. And I would like to explain how to estimate the remainders in the simplest case, A equals 0. Of course, A equals 0 is only the Bogoliubov level of the approximation, and this has been known before. But for any A larger than 0, the notation becomes so long that's like that didn't really fit on the slides. So I think I explain A equal to 0, and then yeah, I think we can imagine how the idea is generalized to large A. Okay, so what we would like to compute is we would like to show that the trace of PA is given by the trace of P0A plus an error term which is of the order lambda to the 1/2. And A is just any bounded operator on Fock space. Okay, so what we do first is we expand the excitation Hamiltonian one step. So we expand it around the Bogoliubov Hamiltonian, and then we write the Taylor remainder here. And then we essentially proceed as I showed on the last slide. So you write the projectors as integrals over the resolvent, expand the resolvent, and so on. And one can then, by some calculations, show an estimate like this. So we get the trace of PA minus the trace of P0A is bounded above. So this sign here means bounded above by some constant times what's on the right-hand side. And here we get lambda to the 1/2, and then we get R0. So that's the remainder here from the Taylor expansion, acting on chi0, the Bogoliubov ground state, times an IA acting on chi0, plus the same with chi0 replaced by chi. Okay, now since we have only bounded interactions at the moment, we can show that this remainder here of the Taylor series, this can be bounded above in terms of the number operator. And now this is very convenient because we know that chi0 is a quasi-free state. And as such, any power of the number operator acting chi0 can be bounded above by some constant. And A is anyway a bounded operator, so this means that this gives a constant, this gives a constant, and this gives a constant. The only thing which we don't know is this one, where we have now powers of the number operator acting on chi. So essentially, we would like to conclude that everything on the right-hand side is of the order lambda to the 1/2. So what we need to show in order to conclude this is that powers of the number operator acting on chi can be bounded above uniformly in N. And for bounded interaction potentials, this is an easy argument, which I would like to show. So we would like to prove that any moment of the number operator with respect to chi, so the true ground state, is bounded above by some constant. And we know, for example, this is shown in the work by Pickl and Seiringer, that the expectation value of the number operator with respect to chi is bounded above uniformly in N. And we also know that the number operator can be bounded above by the Hamiltonian plus a constant. Okay, and now we can prove the statement by induction. So let's look at the B plus first moment. So I split this B plus 1 into B half, and 1. The B halves here are on the sides here, and then the one remaining power of the number operator. For this, I use this estimate here and bound it above in terms of the Hamiltonian. And now I would like to commute the Hamiltonian with the number operator. Okay, then we get first the term where the Hamiltonian is on the right-hand side, which restores a power B here from the number operator and the commutator. Okay, now this here is fine because chi is an eigenstate of H, because chi is essentially the ground state of H. So this will only give ground state energy times chi. And then we have the commutator, And if you compute the commutator, then you will get again from this number operator plus 1 to the power of b half. So in total, you can bound this above by the bth power of the number operator, and this closes the induction. So what we did show with this argument is that essentially any finite moment of the number operator with respect to chi is bounded uniformly in n. And this is exactly what we needed. So combining this with the result we had before, we have now shown that the trace of PA minus the trace of P0A is bounded above by some constant times lambda to the 1/2 times A acting on chi0 plus A acting on chi. And since this is true for any bounded operator A on Fock space, we conclude from this the trace norm convergence here. Okay, so but now we call it our main result. This was for the n-body projector, not for the excitation projector. And also we get a power lambda to the 1/2 better for the n-body setting than in this setting. Now I would like to explain.
Excuse me, what do you use the fact that the potential is bounded?
This is because here, this doesn't hold anymore if the potential is bounded. It's not bounded. But I will comment on this later. Thanks.
Thanks. Yeah.
So because I will talk about unbounded inductions and because there we have to do something else here. Yeah. Okay. So now I would like to prove the statement for the n-body setting. So let's do this for the simplest case. So let's say A is a bounded symmetrized one-body operator. And I would like to compute the leading order of trace of Pna. Okay, now if we do this essentially as we did like in the very beginning, instead of writing Pn, I write P conjugated with the excitation map. And then I also make use of the fact that the trace of P and the trace of P0 equals 1. Okay, now if I write, so the difference between the trace of P UAU star minus the trace of P0 UAU star, then I can of course subtract in both terms here the same constant. And I choose to subtract this constant here. So that's the condensate expectation value of A. So I subtract this constant here in both terms. It doesn't change anything. Then this means that I can write this as the trace of PA reduced minus the trace of P0A reduced. And A reduced is now exactly the UAU star minus this constant. Okay, now this is now really useful because first of all, A reduced is a bounded operator. So this result here applies. So if we, and also the norm of A reduced acting on chi or chi0 will give us another power of lambda to the 1/2. And the reason is the following. So A reduced means that I take this operator A conjugate with n. So if we call the n-body Hamiltonian, there we did the same. So if I do this, then we get a leading order term, which is of order 1, plus next like higher order terms, which are at most of the order lambda to the 1/2. But the leading order term, this is exactly this one, and this is this one I already subtracted. So the next order term is at most of the order lambda to the 1/2. And therefore, we can prove that this gives an additional lambda to the 1/2. So if we then use this and plug this into this estimate here, then we get finally that the trace of P and A is given by the trace of P0 UAU star plus an error which is of the order lambda. So this explains why we get a lambda to the 1/2 better than in this case, essentially because these operators A, they are special operators because they come originally from operators on the n-body Hilbert space. Okay, now let's go back to the main result. So I've explained or sketched how to prove the statement for A equals 0 and for bounded symmetrized one-body operators A. Actually, you can, if you want to have A larger than 0, which is of course the interesting case, then essentially the argument generalizes, just the calculations become much longer. And additionally, we also have to take care to estimate, for example, commutators between resolvents of the Hamiltonian and the Bogoliubov Hamiltonian with powers of the number operator. And we also can extend this to operators A, which are not bounded anymore, and but they have to be relatively bounded, and which are symmetrized n-body operators. Okay, so actually our main result in the paper has some more, is a bit more general, and now I would like to comment on the extensions which are also contained in the paper. And the first extension I would like to consider is concerning the n-body, the excitation spectrum, and not only the ground state. So if I would like to talk about excited states, then I denote by En the eigenvalues of H and by En0 the eigenvalues of H0. But now we have to be a bit careful, because if we do not talk about the ground state, but about excited states, then there can be degeneracy. And in particular, it can happen that the degeneracy changes in the limit where n goes to infinity. So it could happen that we have two different eigenvalues, En1 and En2 of the Hamiltonian H, which are different for any finite n, but which converge to the same limiting eigenvalue of the Bogoliubov Hamiltonian. In this case, if we define by Pn as the integral of the resolvent of the excitation Hamiltonian along this contour around this Bogoliubov eigenvalue, then eventually this contour will contain both the eigenvalues En1 and En2. And this means that we actually, this will be a sum of spectral projectors. And of course, this also translates to the n-body setting. So in summary, our main result is still true, but it holds potentially for sums of spectral projectors. Okay, so the second extension is hopefully now answering Daniel's question, namely what to do about unbounded interaction potentials. So I said before that we do not have to restrict bounded interaction potentials. What we actually really need is that V needs to be even of positive type, and V squared has to be relatively form-bounded by the Laplace operator. But in this more general case, we also need a second assumption. Namely, we need to assume that the n-body Hamiltonian minus the condensate part of the energy is bounded from below by some constant times the sum of the Hartree Hamiltonians, so they are written here, up to an error which grows at most as n to the 1/3 if n becomes large. So before I comment on why we need the second assumption, here are some examples of potentials which fulfill these two assumptions, A1 and A2. Of course, it's clear that this is satisfied for bounded and positive definite interaction potentials. In this case, we actually get the optimal error estimate of epsilon of n is order 1. But it's also true, for example, for the repulsive three-dimensional Coulomb potential. And in this case, we really have the worst possible epsilon, which is of the order n to the 1/3. Now, if you have unbounded interaction potentials, then the proof becomes more complicated. For example, because we can now not bound all the Taylor remainders only in powers of the number operator anymore, but we can only bound them in terms of the number operator and the Bogoliubov Hamiltonian. And what's also becoming much more difficult is proving this estimate for the moments of the number operator. So, and this is, I would like to explain this now because this is explaining why we need the second assumption A2. So what we need for our estimates is that any power of the number operator with respect to chi is bounded uniformly in n. And for bounded interaction potentials, we had this very simple induction argument. But now for unbounded interaction potentials, we still know that the expectation value of the number operator is bounded uniformly, but we do not have this bound anymore. And this is why we now need this assumption A2, which is giving us essentially the estimate that the number operator is bounded above by the excitation Hamiltonian plus n to the 1/3 at worst. Okay, now you can directly see that the induction argument does not work anymore, because let's do the second step of the induction. If I take n number plus 1 squared, then I get already an n to the 1/3, so we cannot close the induction argument anymore. And in this case, now we need to do an additional bootstrapping argument, but in the end, we can also show that this estimate here holds. Okay, so the last extension I would like to mention concerns the ground state wave function. We know that the ground state is unique, and we have derived an expansion for the projector into the ground state. From this, we can now also derive an expansion for the ground state wave function. Namely, we can show that the ground state here, so chi, the excitation part of the n-body ground state, has an asymptotic expansion in powers of lambda to the 1/2. And I've written the coefficients chi L here for completeness, but for example, the first order correction to the Bogoliubov ground state is given by P1 chi 0, so that's the Bogoliubov resolvent H1 chi 0. And if we go from this back to the n-body setting by taking the condensate here back into the picture, then we really get an expansion of the n-body ground state to any precision we want here. Okay. So to conclude the talk, I would like to briefly also talk about the dynamical problem. So the physical situation I have in mind is the following. We start with a Bose gas, which is prepared in an eigenstate of a trap. So let's, for example, for simplicity, just take the ground state. So we start in the ground state of a trap, And about this state, we now know quite a lot from the result I've mentioned before. And now we will switch off the trap and we study the time evolution of the gas. By this I mean that we look at the Schrödinger equation for the Hamiltonian H and free. So that's the n-body Hamiltonian as we had it before with the same interaction potential. Actually, I should say already that the dynamical statement only holds for bounded interaction potentials. Okay, and we do not have any trapping potential now anymore. Now this Hamiltonian has been studied quite a bit. It's, for example, known that condensation is preserved under the time evolution. So this means that we still have at any later time Bose-Einstein condensate, but the condensate wave function evolves with time and is given as the solution of the Hartree equation, which is written here. Now the goal is now that we would like to characterize the n-body wave function at time t, so the time evolved n-body wave function, the solution of this equation here, at any later times. And what we will see is that the structure of the ground state is preserved under the time evolution. And knowing this, we can then also compute, for example, the correlation functions or the reduced densities or any other dynamic quantities of the model at later times and to any order in 1 over n. So what exactly is meant by the structure of the ground state is preserved? Okay, here's the theorem. So we start in the setting where we have the n-body ground state of the Hamiltonian with trap. And we denote by psi n of t the solution of the Schrödinger equation for the Hamiltonian without trap. And chi of t is now the excitation part of this n-body Schrödinger, of this n-body wave function. Then we prove that this chi of t has an asymptotic expansion, also at any later times t, with time-evolved coefficients chi L of t and with an error which now grows also in time. And these coefficients chi L of t, they're explicitly given in terms of phi of t, so that's the solution of the Hartree equation, and in terms of chi 0 of t, that's the solution of the Bogoliubov equation. Okay, and I didn't write down the formula for chi L because they're quite long, but the important fact is that everything is explicit. Okay, so the leading order of this result had been known before. So it has been proven first for this model here by Levine, Nahm, and Schlein in 2015. And later there's also a series of papers by Nahm and Napiorkowski, also for more singular scalings of the interaction. And on the Fock space setting, there is also a very old paper by Ginibri and Velo, and a series of more recent papers by Grillakis, Machedon, and also partially Margetes, where they again consider more singular interactions. And also concerning the higher orders, there are related results. So the first paper is again in the Fock space setting, and that's due to Ginibri and Velo in 1980. Then there are also two recent results for the n-body setting. So in this paper, Paul and Polverenti, they construct an asymptotic expansion of the reduced density matrices. And then we also had a joint work with Natasha Pavlovich, Peter Pickl, and Avy Soffer, where we were also deriving an asymptotic expansion of the wave function. So the difference between this new result and these two papers here, there are actually two differences. So the first difference is that in these two results, the approximations, they were still implicitly depending on n, the number of particles. Whereas in our result, it's chi L of t, this is completely independent of n. So the full independence is only in the prefactor. And the second main difference is that our chi L of t, they're really explicit formulas, which you can essentially compute once you know the solution of the Hartree equation, which is a one-body problem, and the solution of the Bogoliubov equation, which is essentially solving a 2x2 matrix equation. Okay, and now since we know now quite a lot about this ground state, we can compute stuff. For example, the reduced density matrices. So this is like one application of the theorem is to look at corrections to the one-body reduced density matrix. So the setting is again the same. We start in the ground state of the Hamiltonian with trap. We switch off the trap and look at the solution of the time-evolved equation without the trap. And then we prove corrections to the one-particle reduced density matrix. Again, we get an asymptotic expansion at powers of lambda with an error which also grows in time. So for example, let's look at the leading order term here. So the leading order term is of course the projector onto the time-evolved condensate wave function. What's new is now the first order correction to this. And this is given explicitly, it's written down here. So this depends now on phi of t. So that's the solution of the Hartree equation. And on beta of t, so beta is a function which is written down here. You get this when you take the scalar product of chi0 with ax chi1 plus chi1 ax chi0. Then you also have the gamma chi0. That's the Bogoliubov 2-point function. So that's written down here. So it's the chi0 a y dagger ax chi0. And then we have again the p with the trace of gamma chi0. And alternatively, you could also derive a partial differential equation for beta instead of writing this explicitly here. Okay, now, yeah, I will summarize now the talk. So we've considered a system of n bosons and trap with interactions in the mean field regime. Then we've seen that the low energy eigenstates admit an asymptotic expansion and powers of lambda to the 1/2. And the energies can be expanded in a power series, which is in powers of lambda, because all the half integer powers vanish. And then we've also seen that if we switch off the trap and look at the dynamics, then this property of having an asymptotic expansion is preserved. We get coefficients which depend explicitly, which are known explicitly, and which lead, for example, to an expansion of the one-body density matrix at later times. So yeah, and this, I thank you very much for your attention.
Thank you very much indeed for this beautiful talk. Are there questions? So please unmute yourself and ask a question if you have one.
Maybe I have one. Thank you very much, Lea, for the nice presentation. So just somehow as out of a curiosity, so you commented about the fact that this constant goes very bad in the error terms. I guess you expect the optimal constant to be just a factorial, right? And somehow you said that instead you get some exponential of a factorial, if I remember correctly.
Mm-hmm. Yeah, so I'm not sure. So I'm definitely sure that it's not the optimal one, and I think factorial would be oops, what happened now? Yeah, factorial would be more realistic. But actually, the point is that this comes from the method, because what we need to do, maybe I don't know whether, yeah, okay. What we need to do in order to show our estimates is we need to always commute number operators with Bogoliubov resolvents, and then each time we commute the number operator, we get essentially a very bad constant, because we look at how the Bogoliubov transformations transform the number operator, and then we get the number operator times some constant back, and then we get this constant in each step, and this is just behaving very badly. So this is why I definitely expect this is not the optimal rate.
Mm-hmm. Okay, thanks.
Thank you. Further questions?
I also have a question. This chi L, like I know it's explicitly given in terms of the Hartree and the Bogoliubov functions, but does it satisfy some nice function even in an approximate sense? Does it satisfy a nice effective equation itself?
Yeah, that's an interesting question, which we would like to look into. So at the moment, I have no answer to this yet. So I can only give you, I can show you, for example, the explicit form, but it's not. It's what you are proposing is really what we are also looking into at the moment. So just maybe okay. So if let's say we start in the ground state of the Hamiltonian. Okay, then we can write. So I didn't make this explicit, but schematically we could write the chi1 of 0 in this form, that we get operators B acting on and plus up B1 and B3. Okay, just schematically. And if we would start with such an initial data, then we get as a time evolved initial data this formula, where we have now coefficient C, which we get by these are the coefficients of the Bogoliubov map acting on this B1, which are the coefficients from here, and B3 and so on. So this is at the moment how we can compute these operators chi L, but finding an effective equation would be really nice indeed.
Thanks.
May I ask?
Yes, Jakob?
May I ask a question? Well, actually, I have two questions. The first is always the same, namely about the time dependence. I guess it is here the same as usual, that the estimates for for how long these bounds hold, they will blow up very strongly with the temperature, isn't it so? Or do you have any improvements on that?
No, not yet. So we only try to get the estimates in n, and we just didn't care so much about this constant here.
Because
it's only short time.
This CA is very bad. It goes like some exponential.
Yeah, it's really bad, right? Yeah. So you have to read the result as let A fixed and then let n be large enough. Yeah, this would be very very interesting to improve this, but with our method, I don't think it will work.
And then a second question, I'm getting a little bit confused about the state of the art now, because so this is all this mean field, the Hartree theory, but there are also results about more singular dependencies on n all the way up to Gross-Pitayevsky, isn't it? Gross-Pitayevsky scalings, or how does that compare with these results? So these are, I mean, there are recent papers by, well, as you know, of course, by Schlein and his group, and also by Nam and his group about the Gross-Pitayevsky theory and the estimates of the excitations.
Yeah. So this is at the moment only mean field, and would of course be very interesting to go to more singular interactions, but of course much more difficult as well. So I think Gross-Pitayevsky, they basically do the leading order, so at least in the not in the dynamical but in the static setting, but not higher orders. Of course, this is an interesting direction of research, and we try to do to get our interactions more singular, but it's not so easy.
Yeah, so the main achievement here is to get to these higher orders.
Exactly. So this is everything is only mean field, but the new thing is that we now get like essentially any precision you want, but only for the mean field.
Okay, very good. Okay, thank you. Thank you, by the way, for the beautiful talk.
Thank you. Further questions?
I have a question. You mentioned low-lying excitation spectrum, but did you formulate the result about these low-lying eigenvalues? I mean, so for instance, what is the range of eigenvalues that you have good estimates for?
So essentially order 1. So
order 1 means how many? I mean.
Okay, so in this constant here, this depends. There's also basically the energy of the eigenvalues. Like there's in this constant here, there's hidden like an modulus of the energy of the eigenstate. So this means as soon as this is of order 1, it's okay. Yeah, depending. And so anyway, fix an eigenstate, then you just have to be n has to be large enough.
Yeah. So I mean, if you how many eigenvalues can be covered in your result? I mean.
Yeah, this depends on n. So I can like if I take the kth eigenvalue, then I will have here the energy of the modulus of the kth eigenvalue will be in this constant here. So therefore I have to choose n large enough.
So you fix the number of an eigenvalue, and then you have then you can find n large enough so that you have a good estimate. Okay.
Yeah.
Yeah. So I mean the thing that interests me most in this is the kind of large volume limit. So you suppose you have periodic boundary conditions. So you have a torus, and you try to make the dimensions of the torus big enough. What would be the I mean? What are the error terms? What is the dependence of the error terms on the size of the trap?
Yeah, this is also a question which I cannot answer, but it's also an interesting question which we're looking into. So what would happen if you go to the large volume? So I think I cannot answer this at the moment, but I would like to.
Thank you.
Thank you. Other questions?
Somehow it seems counterintuitive that like the better precision you get, the worse the time dependence of the error becomes. Like somehow you would hope that if you compute your dynamics to a higher precision, that you could like extend it for longer times. But yeah, just by like summing the error terms in another way, I guess. But yeah.
Yeah, that's true. I think that's just our method is just not good enough because we didn't care about the A dependence, and like this commuting of number operators with resolvents is just not optimal. So, but yeah, I agree. It's somehow counterintuitive.
And then on the volume dependence, what are the powers of the number operator that you get for the error terms? Because that tells you the dependence on the volume.
So this depends again on the power of the number operators depending on A, but I don't recall exactly which power we have. Yeah, sorry, this I would have to look up myself.
Thank you. And so in principle, you could also consider a homogeneous gas with these kind of techniques.
Yeah, so we did before, but then it also works in the external with an external potential, but it makes only things easier if you have a torus. Just I think this with an external trapping is just more realistic, so that's why we chose to write it in this way.
And in terms of its potential, so it can be unbounded, but it has to be relatively bounded with respect to the Laplacian. Clearly, you must have a condition because a hard core, for instance, will not work. I mean, or unless you would also renormalize the radius of the hard core. But could you go beyond this restriction of being relatively bounded by the Laplacian?
I don't think so, because what's why we need this is essentially because we get these estimates, so we get these remainers in the Taylor series, and there will be a term where we have the second quantization of the interaction potential. So because there all the other terms there we have also a condensate wave function. We can like, if you have a condensate wave function, then you can apply Laplace on the condensate wave function, everything is fine. But if you have now this second quantization of the potential, there's no condensate wave function in the term. So we somehow need to bound this in terms of the Hamiltonian itself, of the Bogoliubov Hamiltonian, because this will then again act on the state. And this is why we need this assumption, because we somehow need to get this term where we have only the second quantization of the interaction bounding in terms of something which acts finitely on the state. And therefore, I don't think we can extend this much beyond, at least not with this method. So you would have to come up with something else.
Yeah, thanks. Yeah. Other questions? If not, thank you very much, Lea, for this talk.
Yeah, thank you.